Linear differential equation, shortly can be called LDE. dy by dx plus py is equal to q. So this is the general representation of linear differential equation, where p and q are constants or functions of x only. Now dy by dx, let me explain with an example. What are the different types of equations adopting this form? Dy by dx plus xy is equal to cos x. Now what is p here? X. What is q? Cos x. Okay. Now dy by dx plus y by 1 plus x squared plus that is equal to x. Now what is p here? 1 by 1 plus x squared. Okay. And x is the q of x. The dy by dx plus y is equal to e power x. Okay. Now what is p here? 1. Very good. And what is q here? E power x. Okay. Right. Now let us have another form, that is dx by dy. Here dy by dx, here dx by dy plus px. Px actually that is x. This p is the coefficient of x. Now px means this is equal to q, means p and q are the constants or the functions of y only. In this case they are the functions of x or constant, whereas here they are the functions of y or constants. Are you able to understand? So let us cite some examples like dxy, dx divided by dy plus x is equal to sin y. Another example, dx by dy plus x by y squared is equal to e power y. Are you able to follow? Right. Now let us try to solve the LDE of type 1, that is dy by dx plus py is equal to q. Now there are some key steps. The given equation should be converted into the standard format like this, and based on that you must be able to identify the type, whether it is type 1 or type 2. Second, you have to determine the integration factor. So IF means integration factor. So the integration factor is nothing but IF is equal to exponential, that is e power integral p dx. Is it clear? Right. Now the solution can be approached like this, forming this type of equation, that is y into, you have to bring this IF, which is nothing but y into e power integral p dx. Okay. That is equal to integral q into IF of dx plus c. Then we can proceed. And let us talk about form 2. How about the form 2, that is dx by dy, is it not? So we have taken and dx by dy plus a px is equal to q. In that case, instead of integral factor e power p dx, integral p dx, he had to put integral e power minus e power integral p dy. Okay. And you can proceed like this. Instead of y, you can put x into integration factor, that is equal to integral q into if dy plus c. So this is the way you have to solve this equations. Okay. Now let us explain with an example. Let me proceed with form 1, type 1, dy by dx plus py is equal to q. Now solve the differential equation given cos squared x into dy by dx plus y is equal to tan x. What we are supposed to do? This is a given equation. We had to convert this into this form. So you can divide the entire equation by cos squared x, because we had to isolate this dy by dx. So 1 by cos squared x, apply on both sides. So that cos squared x can be cancelled. So dy by dx. Got it? And y by cos squared x, that is equal to tan x divided by cos squared x. Got it? Now You know very well 1 by cos squared x is nothing but secant squared x. So secant squared x. So dy by dx plus secant squared x into y, and that is equal to tan x. So you can put 1 by cos squared as secant squared x. So secant squared x into tan x. Are you able to follow? Now the general form is given here. Dy by dx plus f of x of y, which is nothing but py, that is equal to g of x, which is nothing but q. Now tell me, what is p? Secant squared x. What is q? The secant squared x tan x. Okay, right. Now we have to find out the integration factor. So that is equal to e power integral p dx, is it not? So you can apply e power, and this p dx is nothing but secant squared x dx. Okay, so secant squared integral is tan x, therefore integral e power tan x. We have got p is equal to secant squared x, and on the RHS we have got tan x into secant squared x. You can put that one. So we can apply this equation. So y into integration factor. So y into e power tan x, that is equal to, you can put all this, tan x into secant squared x into e power tan x, because ef, that is integration factor, should be multiplied here, followed by dx. Okay, now you have y into e power tan x and the integral tan x. Then you can bring this e power tan x here, and you can isolate this. So put secant squared x dx here. Now we can adopt some substitution technique. So tan x can be taken as a z and differentiate this. So secant squared x dx is equal to dz. So we can replace this. For example, y is equal to e power tan x. Instead of tan x, you can put z. So y into e power z. Got it? On the RHS. So integral, and instead of tan x, you can put z. Instead of e power tan x, you can put e power z. And you got already that is a dx. Okay, so secant squared x dx is equal to dz. You can simply replace this dz. Got it? Right. Then now we have to proceed by the integral by parts, because it has got two functions, is it not? So y into e power z minus, and this is the z into e power z. So you can take u and v. So we have got uv minus v du. Are you able to follow? So we have now v du. So v is e power z. So e power z into dz. Now z e power z, and e power z on integration gives e power z only. So minus e power z, and then plus integral constant. Now we already know tan x is equal to z. So let it be as such. Don't confuse here. Now y into e power z is equal to, e power z is common, so you can take outside the bracket being the GCD. So z minus 1 of e power z plus c. Now y z, and you can divide by e power z on both sides. So it becomes what? Y e power z cancel. So z minus 1, and this is also cancel. Now you have got c divided by e power z. So which is nothing but, now tan x is equal to z. So you can put y instead of z, you can put tan x minus 1 plus c divided by e power z. Instead of e power z, you can put tan x, e power tan x. Okay, so e power tan x means that is e power minus of tan x, that is nothing but tan inverse x. So this being constant, you can make it as a constant. Now the value is y is equal to tan x minus 1 plus the respective constant. Okay.